In this lesson, we're going to review the sine law, and we're going to look at something called the ambiguous case of the sine law. So first of all, the review part. Remember, the sine law is a formula for calculating the side lengths and angles for non-right angled triangles, sometimes called oblique. And remember, just for as far as labeling triangles go, we use capital letters for the vertices, the corners, in other words, where the angles are. And then we use lowercase letters, actually let's do it this way, lowercase letters for the side across from an angle. So big A for a corner, and then little a for the side across from it. So big B is across from side length little b. Angle big C is across from side length little c. And then the sine law tells us that if we do a side length divided by the sine of the angle across from it, then it's going to be, they're all going to be equal proportions. So A over sine A is equal to B over sine B is equal to C over sine C. And we also know that we can flip each of these fractions upside down, and they're still true. So sine A over this of length A is the same as sine B over B, and so on. So that's the sine law. You must know an angle and the length of the side opposite from it in order to use the sine law. In other words, we never use all three. If we just look at this part, this first version of the formula here, we never use all three fractions. So we might use these two together, or we might use these two together, or we might use the first one and the third one, but we never use all three of them at once. Let's say we were using these two fractions that I just circled. You can see there's four parts to it. There's side length little a, there's angle big A, there's side length little b, there's side angle big B. If I know 3 out of those 4 values, then I can find the fourth one. And so I need to know things in pairs. So if I'm going to know 3 out of the 4, then maybe I know A and, side length A and angle A. And then I can compare it with any other one missing thing and then make a second fraction. So here's a couple of sine law questions where they're pre-set up for us. We've got, it doesn't give us a triangle, of course, it's just got the values filled in. So supposedly we know a side length and then the angle across from it. And we don't know this side length, but we do know the angle across from that. So this is something we can solve. So the goal, of course, is to isolate the variable. And the way we do that is we multiply both sides by whatever's on the denominator. In this case, it's sine 48 in the denominator. I'm looking to isolate the b. So I'd multiply both sides by sine 48. And the way I'd write it is 65. I'd leave the 65 on the top, times sine 48. That would go up into the numerator of the other fraction. Leave the sine 75 on the bottom, and b is by itself. As long as our variable, in this case b, is on the top, we can always do it that way. In other words, what will always happen is whatever's in the numerator ends up in the whatever's in the denominator, of the side I'm trying to solve ends up in the numerator of the side, the other fraction. So I got 65 times sine 48. And I think it was divided by sine 75, but I'll have to confirm that. Sine 75. 65 times sine 48 over sine 75. Calculator set to degrees, I got 50. So b equals 50. Whatever the units are, that wasn't specified, but that's my answer. So I just rearrange. Now, I would never set up a sine law question the way it is in B part, and I'll tell you the reason why. I would never put the variable on the bottom. It's just so much easier to work with it if it's on the top. So if I'm given one like this, the first thing I do is just flip the top and the bottom for both fractions to get my variable on the top. And then I want to isolate A. So then I would bring this 75 to the top of the other fraction, basically make it a multiply 75 times sine 80. And that was divided by 100, if I recall correctly. And I've got a decimal, 0.7386. And the reason why I've got a decimal is because I have one more step to do, right? I haven't isolated a yet. I still have to take the inverse sine of that, sine with that exponent -1 of 0.7386. And so I've still got that in my calculator. I can go inverse sine, and I can go back to my answer, 47.6. And that would be degrees. Angles are always in degrees, at least this year. So there you have it. Solve for the following triangle, solve for side C. Okay, so when I look at this triangle, the first thing I notice is that I know side A, and I know an angle and a side across from it. That's my look for. I look for an angle with a side across from it. I'm supposed to find side C. But in order to do that, I would need to know angle C first, and I don't. And I don't have a way of getting angle C, at least unless I find angle B. So sometimes I have to find extra values so that I can then get to what I want. So in order to find side C, I'd have to know angle C, and in order to get angle C, I have to know angle B first. So I have to do a couple of calculations. So I'll start with A and B. So to find side B, or sorry, angle B, I'd do sine B over 14 equals sine 51 over 19. I'd bring that 14 to the top of the other fraction and work out what that is. So 14 times sine 51, I'm just going to reuse this. 14 times sine 51, and I'm going to divide that by 19. So I just changed the numbers on my middle line there. And I got 0.5726. And then that means that B, angle B, is going to be the inverse sine of that. And I already have that on my calculator as well because it just changed when I changed my other numbers. 35 degrees if I round it to my nearest degree. Okay, so I've got 35 degrees for angle B, which is great, but that's not what they asked for, of course. But the reason I wanted to find it is because now I can get angle C. Since we know that all angles in a triangle add up to 180 degrees, then I can just subtract the angles I know from 180 to see what I've got left. Let's see, 51 and 35 is 86, so I guess I could do this in my head. It would be 94 degrees. So I know that angle C is 94 degrees. Now I've got what I need in order to find side length C, which is what they asked for. So I can go again to the sine law, C over sine 94, since that's what angle C is, equals 19 over sine 51. Bring the sine 94 up to the top of the other fraction, and so it's 19 times sine 94. Again, I'll repurpose this. 19 times sine 54. 94, sine 94. 19 times sine 94 divided by sine 51. And I got 24.4. And the unit is meters because the original 14 for side little b was in meters. Okay, so that's a quick review of the sine law. We can use it for finding angles, and we can use it for finding side lengths. So what is this ambiguous case of the sine law? Well, let's start with a challenge. Given a triangle ABC, so that you can see it there, if it's got side A is 4 centimeters, and side B is 5 centimeters, and angle A is 45 centimeters, sorry, 45 degrees, is it possible to keep the measurements the same and draw another triangle? Well, just to cut to the chase here, the answer is yes. What if I were to draw it like this? And I kept this as 45 degrees. And I kept this as 5 centimeters. And I kept this as 4 centimeters. What's changed are the other three parts, right? This is still A, still 45, so it looks like 45 approximately. But C, which used to be a big obtuse angle, is now a tiny little acute angle. And B, which used to be a little acute angle, is now a big obtuse angle. And side length B, which used to be quite long, is now quite short. So if those all change, it's possible to draw another triangle keeping those particular dimensions the same. So how do I know if it's possible? Because it's not always going to be possible if you're just given some dimensions. Well, one way to do it is to imagine that, if we look at this triangle here, imagine it's an actual, maybe it's made out of pieces of wood, okay? And up here at the top, imagine there's some sort of hinge. And so this side A is actually on a hinge, and it could swing back and forth, provided it doesn't scrape on the floor or something, and go to different places. And if it's a particular length, maybe I could swing it in here. Okay, so that's the way I want you to think about this. Depending on how long A is, I might be able to tuck it underneath. It might be, if it was exactly the height of the triangle, I might make actually a right triangle out of it. I might just go right here, or I might not be able to get it in underneath, depending on again, what the side lengths are. So one thing in order to answer this is it all depends on the height of the triangle. And the height of the triangle here is represented by the letter H. So picture this right triangle. Let's take a sub-triangle here. Here's a right triangle. And in this right triangle, H represents the opposite side. B is the hypotenuse. And A is, of course, the angle. So sine of A, we know that sine equals opposite over hypotenuse. So sine of A is going to equal H over B, my opposite and hypotenuse sides. Let's get rid of these because this is cluttering things up for now. Maybe not. Let's leave them there for now. If I were to rearrange this formula to try and isolate H, I would just bring the B out in front, I'd multiply both sides by B, and I'd get H is equal to B times sine A. So if I know what angle A is, and I know what side B is, and I will in these situations, then I can find out what the height of the triangle is. So using this formula, so keep that in mind, H equals B sine A. Let's take a look at some different cases. So the first case, what if side A is shorter than H? So here's a sketch, but the sketch could be false. In other words, only rely on the values given. So we're given this length is 15, we're given this angle is 16, we're given this side over here is 3. Maybe the sketch won't actually look like that. So if this side A, remember this is little a over here and this is side B, if side little a is shorter than H, the height, I can't even form a triangle. It's just going to, remember that hinge idea? It would just sort of dangle here and never actually make it to the floor. It would just sort of swing back and forth like a pendulum. And, obviously this part of the triangle would not even exist. What I would have is an incomplete triangle with this 3 centimeter long, or meter, or whatever the units are, piece just sort of dangling here, not even making it to the opposite side to complete the triangle. So that's one case. If A is shorter than H. If A is the exact same length as H, then what we're going to have is a right triangle, right? Because if A is the same length as H, it's going to dangle here from C, to continue that metaphor, and it's going to come right down and touch this side here. And again, it's not going to be out here the way I've got it drawn. It's going to be a perfect right triangle because of what just happened. Because of H being exactly the length of A. So we can have, it's possible to have a right triangle if A equals H. It's possible to have a single triangle, it's not a right triangle, if A is longer than side B. And again, keep this idea in mind. These sketches are not to scale. Take a look at side A and side B. If you look at the way it's drawn, clearly B looks longer than A. But if you look at the numbers, 20 is longer than 15. So this is not drawn to scale. If A is longer than B, then there's no way that I could tuck this, again, think of this like it's a swinging side on a hinge. There's no way that I'd be able to tuck it up underneath here because it's too long to fit. So there's no triangle. Oh, sorry, there's one triangle, and it has to be this way. Only it wouldn't look like that. It would look more like this, with A being longer than B. So this is what it would actually look like if it was drawn to scale. And the last case is you could have two triangles. This is what we started off with. This is sort of the ambiguous part. Let's highlight this here. And that is if A is in a certain range. If A is longer than the height, so that it does form a triangle, but shorter than B, so that it tucks underneath, then I could have a sketch that looks just like the one we have here, or I could have that other one that looks like that one I drew up above. You know, this could still be 40, this could still be 27, and this could still be 22, but it's sort of tucked underneath. So then you've got two different triangles, and it's going to have different values for angle B, angle C, and side C, and so on. So the first thing we want to be able to do is determine the number of possible solutions. And so this is given in terms of A and B, but it can be any letters. So this one, for example, is turned around a little bit. We still have angle A and side A, but instead of being side B, this is side C because it's across from, oh, sorry, it is not. My bad. Save that for the next example. It is side B there. So it is exactly the way we talked about it. So I just need to find out what's the height of this triangle, right? And height is equal to B sine A. That's our formula for today. B was 8.4. A was 68 degrees. B sine A, 8.4 times sine 68 equals 7.8, let's call it. Okay, so what? What does that prove? Well, this is where we go back to our different cases and we compare them. How does A compare to H? How does 7.2 compare to 7.8? A is less than H in this case. In other words, A is not even long enough to complete the triangle. I can't even get from C down to the side length side length C. So no triangle. Now here's a case where, that I started to see for the other one, it doesn't have to be A, B, and C. It's just got to be, here's the side and angle across from each other, here's the other side. It doesn't even matter which way the triangle's turned. This is the side that I'm always concerned about. Is that one going to tuck underneath or be long enough or whatever? So the height, I won't even worry about what letters I call it. It's going to be the other side, the 12.4, times the sine of the only angle I have, which is 26 degrees. So 12.4 and 26. And that's 5.44. So that's the height again. So how does A, in this case, M, compare to the height? Well, it's longer, so it's going to form at least one triangle, but it's also shorter than that other side length. So this is one of those cases where it could be drawn the way it's shown, but it could also be tucked up underneath. I'd say that M is greater than H, but less than N, which is what the green one was. So we can form two triangles. It's case 4. So two ways of drawing this. Here's one where it is turned around. Again, let's not get hung up on the orientation. I've got the angle and the side across from each other. I've got the other angle. This is the one that I need to compare to things. The height is going to be formed by doing 10.6 times the sine of 30 degrees. Which is 5.3. And that is the same as what little p is. So this is one of those cases where the comparison side is the same as the height, so it's going to form one right triangle. And let's go back to our original challenge question and see if, check the numbers on it. So now we know there's A and A, there's side B. The height is going to equal 5 times the sine of 45 degrees. Which is 3.5. So, in this case, little a is greater than the height. 4 is greater than 3.5, but little a is less than b, the 5 centimeters. So, this is the case where there will be two triangles. So there's two things going on in this lesson. One is just a review of sine law, which you definitely need to be able to use, and the other is recognizing that in some cases, the information given is ambiguous. Ambiguous means it's not quite clear. So sometimes the information given is ambiguous and you could form more than one triangle with the information given. And if that's the case, if it asks you to solve in the ambiguous case, you really should solve for both triangles.